So this chapter is kinematics of motion in a straight line. So let's look at the theory over here. Part 1, distance, position, and displacement. Okay, distance, position, and displacement. So let's take a look on the theory over here. The total distance traveled by the marble at any time does not depend on its direction. It is a scalar quantity. It is a scalar quantity. So that means if let's say you have a marble, okay, your marble moves to the right by 3 meter, or your marble moves to the left by 4 meter. So the distance is 3 meter, and for the second case, the distance is 4 meter. The direction does not affect the distance. Okay, so we move on to the second part, positions. Position and displacement are two vectors related to distance. They have direction as well as magnitude. Okay, they have direction as well as magnitude. So it is a vector quantity. Okay, so to know about position and displacement, we can see the example given at the bottom here. Okay, so let's see this example. So you look at this picture here. What we have is we have our hand is here, and let's say we are throwing up a stone or a marble. So the marble move upwards. Okay, as you can see from here, it moves upwards to the top until here. You see that they write down the position. The position is positive 1.25 meter. Okay, so position is from here to that side, positive 1.25 meter. Okay, then after that, from here, it drops until here. So they call it zero position. Zero position. And it continues to move downwards and so on. Okay, now let's see the idea here. It's written over here. A position is always referred to a fixed origin. So the fixed origin is here, your hand here. But a displacement can be measured from any position. Displacement can be measured on any position. That's the difference between position and displacement. Both are vectors quantity, but position must start from the fixed origin. Displacement can start from any position, can start from any point. Okay, so when the marble returns to the level of your hand, its displacement is 0 relative to your hand. So you have to mention where you start, okay, where you start, because you can start from any point, right, for displacement. So if you say I start from my hand, then when the marble reach here, this is called 0 displacement. If you start from here, okay. So of course, displacement, like what we said, we can start from any point. We can start from the top. If you start from the top and come down here, then the displacement is negative 1.25. So can start from any point. But negative 1.25 meter relative to the top. Relative to the top means our displacement, like what I said, can start from any point. You start from the top, then your displacement is negative 1.25. Okay? But position is different. Positions, you must start from a fixed origin. So position here, positive 1.25. Position here, 0 position. Okay, so that is the difference between position and displacement. Okay, so on this page, we have speed and velocity. So speed is a scalar quantity and does not involve direction. Okay, does not involve direction. So we have to know the basic concept here. Speed is distance over time. So the distance is a scalar quantity, and the time is also a scalar quantity. Okay, so that is the formula for distance, the formula for speed. And now let's move on. Velocity is the vector related to speed. Now, velocity is, okay, so let me write down here. This is the second formula. Velocity is displacement over time. Displacement over time. Okay, now let's move on. Its magnitude is the speed, but it also has a directions. Okay, so that is the difference between speed and velocity. So let's see one example. If I have an object move to the right 3 meter in 5 seconds. Okay, so the speed is 3 over 5, which is 0.6 meter per second. The velocity is positive 3 over 5, which is positive 0.6 meter per second. So we use positive to represent the direction. So if you have an object moving to the left, let's say 2 meter in 10 seconds. So the speed, we don't care about the direction, so it's 2 over 10, so which is 0.2 meter per second. But the velocity is negative 2 over 10, which is negative 0.2 meter per second. Okay, now let's move on. Number 3, distance time graph. Distance time graph. So the gradient of this graph represents speed. Okay, one quick example. Let's say if you have distance versus time. Okay, so let's say for example, we start from origin. So somebody walk to the school and then study in the school and then go back home. Okay, let's say the time span in second is 500 seconds. Okay, the meter, the distance is in meter. Let's say it is let's say 200 meter. 200 meter. So after that, stay in the school, okay, until let's say 6,000 seconds, and then walk back home in 800 seconds. Okay, so something like this. So you can count the speed. Okay, if you have this graph, you can count the speed. Let's say this point is 0, and let's say this point, okay, this point is called O, let's say O, and let's say this point is A and B and then C. Okay, so to find out the speed when you go to school, so we just count the gradient here. So the speed is equal to gradient. So to find the gradient, we do the gradient formula like this. Okay, so point A has coordinates of 500 and 200. Point O has coordinate 0, 0. So we apply gradient formula, we minus. So we will have 200 minus 0 and 500 minus 0. So which end up with 2 over 5. That is 0.4 meter per second. Okay, so that is the speed when you are going to school. And for the speed where we come back from the school, let's say this one, the speed. Okay, so again, we have to use the gradient. So this is 6,200 and C is 6,800, 0. Okay, so when we count the gradient for this situation, right, you will get a negative gradient. Okay, you get a negative gradient because the graph go down, but speed is a scalar quantity. So you have to purposely put a modulus there to avoid a negative value. Okay, so 0 minus 200 over 6,800 minus 6,000. Okay, we put a modulus there, and after that you get negative 200 over 800, so which is 1 over 4, which is 0.25 meter per second. Okay, so that is the speed. Of course, if you go and count the velocity, so the velocity for this case is, velocity consider the direction, and this is going back. So the velocity is negative 0.25 meter per second. Whereas for the case just now, for this case, going to school, the velocity is positive 0.4 meter per second. So we use plus minus to represent the direction. So that means for distant time graph, you can use the gradient to find the speed or the velocity. Okay, so now let's move on to the next one, number 4. So number 4, we have average speed and average velocity. So average speed is equal to total distance traveled over total time taken. Okay, so for example, let's say for this case, you already know how to find the speed for one particular part and this particular part. So that is finding the speed part by part. But when we come to average speed, we have to find total. So total distance traveled. Okay, so as you can see here, they are going to the school 200 meter and then not moving, and then come back another 200 meter. So the total distance traveled is 200 plus 200. So let's take a look here. So average speed is 200 plus 200. The time taken, so we don't care whether you are moving or not. Like for example, like here, you are not moving, you're staying in the school and study, let's say, for example. Okay, so we just care about the total time span during the whole journey, which is 6,800. So we divide by 6,800, and then, okay, let's see, just quickly count this out. So the average speed is 0.0588 meter per second. So which is much more smaller compared to the speed that we count just now, where we count it part by part, 0.4, 0.25. Okay, but this one is 0.0588. This is much more smaller because it includes the part where he remains stationary in the school. Okay, so now how about the next formula, this one, average velocity, displacement over time taken. Okay, so for this case, if we start from, if that student start from here, go to school, stay in the school and come back, at the end the displacement is 0. Okay, the displacement is 0. So the average velocity is 0 over 6,800. So of course, the average velocity is equal to displacement over time taken, and displacement is 0 because the starting point is your house, the student's house, and then at the end, he come back to the house again at point C. He come back to his own house. So the displacement is hence 0. Start from the house and end up with the house. End up at his own house. So 0 displacement. So because of that, the average velocity is 0. Okay. So that is example. Now let's move on. Number 5, velocity at an instance. So what I said here, you can find the velocity at an instant of time by drawing a tangent. So something like this, let's say, if let's say your graph is a straight line graph like here, so drawing tangent is kind of meaningless here, because if you want to find the velocity at this instant, so the tangent is basically the same gradient as this line, where you can take 0.4 straight away. So that's why if it's a straight line, drawing a tangent on this line doesn't really meaningful. So you can just take 0.4 straight away. If they ask you to find out the velocity at this instant, of course here is horizontal, then the gradient is 0, so the velocity is 0. But if they ask you to find the velocity at this particular instant, let's say at the time of 6,500 seconds, then drawing a tangent is not meaningful here, because the tangent has the same gradient as this value, negative 0.25. So for straight line graph, velocity at an instant is just similar to the gradient of that straight line. But when it comes to a curve, right, let's say if you have a curve, okay, let's say this is distance versus time, and you have a curve. So this curve means acceleration happen. So let's say the car is accelerating, it's moving faster and faster. And if you want to find out the velocity at an instant, let's say at 10 seconds, how fast is the car? Then you have to draw a tangent here. So a tangent is drawn in this way, touching the graph at this particular point, and then you can build a right angle triangle, and after that you can count the gradient of that line by considering two suitable points that you can read coordinate easily, like here x1 y1 and here x2 y2, and then you use the gradients formula, and the gradient represent the velocity, okay, represent the velocity at an instant. Okay, so now we already know a different way to find speed and then velocity, and there are average velocity and velocity at an instant. Okay, so let's move on. Now, number 6, accelerations. So average acceleration is equal to change in velocity over time taken. So if you are taking physics, this formula should be something that you learned long time ago. So like change in velocity is final velocity over initial velocity divided by time. So that is the average velocity. Now let's see the picture here. It's like summarize up everything. So for position, remember, must start from fixed origin. So let's say this is the fixed origin. On the right of the fixed origin, the position is positive. On the left of the fixed origin, the position is negative. Velocity, when the object moves to the right, positive, and when the object moves to the left, negative. Okay, accelerations. So accelerations, we have the first situation here. The object is moving to the right. The speed increases. That is positive acceleration. If the speed decreases, that is negative acceleration, which is decelerating, okay, or decelerations. Okay, so that is the normal one. But when it moves to the left, everything will be opposite already. everything will be opposite. When the object moves to the left and the speed decreases, the acceleration is positive. Okay, so if the object moves to the left, but the speed increases, the acceleration is negative. It's negative. Huh? So let's say I give one example here. Okay, one example for this situation. Move to the left. Move to the left is a bit special here, so I need to highlight a little bit. Let's see one example. So if the object moves to the left, and initial velocity is, let's say, when it moves to the left, the velocity will be a negative value. So initially it's very fast. Let's say negative 10. Final velocity, and let's say it slowed down to negative 2. So negative 10 means the velocity is 10 meters per second to the left, or the speed is 10 meters per second. Okay, 10 meters per second. So that is fast. Final velocity negative 2, that means the speed is 2 meters per second, so which is slow. So this is speed decreases. So this is u. Initial velocity is known as u, and this is known as v. So a equal to v minus u over t. Okay, let's say the duration for this situation from the initial velocity to the final velocity is, let's say, 10 seconds. 10 seconds. So a is equal to minus 2 minus negative 10 over 10. Okay, so end up with 8 over 10, which is 0.8 meter per second per second. Okay, so you will realize that speed decreases here. Speed decreases here, but the acceleration is positive. So something like that happened. Okay, so let's say one more scenario. Let's say this is the first one. Okay, let's say one more. Okay, let's see about the situation where the speed increases, but the object is moving to the left. Okay, so it's moving to the left again. Okay, now let's say initial velocity is negative 1 and final velocity is negative 5, and this happened in 10 seconds. So in order to count the acceleration, we use v minus u over t. So the v is minus 5, the u is minus 1, the time is 10. So you will end up with negative 0.4 meter per second. Okay, so what am I trying to say here is the speed is increasing. Okay, the speed is increasing, as you can see here, from 1 to 5. And that is acceleration. So accelerations to the left will take a negative value. Okay, it's a negative value. So when it's to the left, everything is opposite. Okay, so number 7 here. Using areas to find distances and displacements. Using areas. So we use the area for speed time graphs, not for distance time graph. Distance time graph, basically we find gradient only. Okay, the gradient means something. But for speed time graph, the gradient means something. It means acceleration. And of course, the area means the area is the distance, okay? The distance of the objects, okay? The distance traveled. So you can see here, many of these graphs consist, okay, hold on, I should make it bigger. Okay, so let's see. Many of these graphs consist of straight line sections. The area is easily found by splitting it up into triangles, rectangles, or trapezia. So you can see here, if you have a triangle, so we can find the area easily, 1/2 base times height. So if it's a rectangle like this, we can find the area easily. So it's just velocity multiplied with time. If it is a trapezium, so we just do 1/2, add up the parallel sides, then multiply with time. Okay, so multiply with the base. Yeah, so we can find the area easily, and the area represent the distance. Okay, the distance. So let's see the next one. Okay, so here, number 8, the area between a velocity time graph and the time axis. Okay, now the area between a velocity time graph and the time axis means the horizontal axis, represents the change in positions. That is the displacement. Change in position is the displacement. Position is basically start from origin and go to a particular point. So change in position is displacement. Okay, so speed time graph. Speed time graph, you can see here. Okay, so they already count out for us this rectangle. The area is 12. As you can see here easily, 6 times 2, which is 12. And for this part, so this is another rectangle. It's just 2 times 1. You get 2. So the total area is 12 plus 2, which is 14. And this is also the total distance traveled. So the total area is the total distance traveled. Okay, so let's see the next one. This is speed time graph. So basically, we have to say that speed time graph, the area represent the total distance. For speed time graph, area represent total distance. Okay, so now let's move on. The next graph given is velocity time graph. For velocity time graph, you can see here, the area over here represent displacement. And this area, if you go and count the area, so you end up with -2. So you have to consider the plus or the minus when it is velocity time graph. So when it's below of the time axis, so the area here, you have to take -2. So if you total up these two, you will get 12 minus 2 equal to 10. And that represents a displacement. Of 10. So the movement will be something like this. Let's say, imagine, okay, I draw out how it moves. So it will be like this. The particle moves to the right for 12 meter. So after that, you turn and go backwards by 2 meter. And the displacement is 10 because we count from here all the way to here. So that is displacement of 10, positive 10 meter. So that is the idea of what happens here. Okay, now we have the summary. You see the graph. We have position time graph. So position time graph, this is the initial positions, and then the graph is like this. So you know position is a vector quantity. So a vector quantity, if you go and find the gradient, you get velocity. The area, nothing useful. Okay, nothing useful. But you see distant time graph. Distant time graph, the gradient is the speed. The area is nothing useful. Okay, so you see velocity time graph, the gradient represent accelerations. The area represent displacement. Okay, you will have a negative area sometimes. Okay. For speed time graph, of course, speed is a scalar quantity. That means your graph is always positive. They never go below of the t-axis for speed time graph. So the gradient represent the magnitude of acceleration. So that means they ignore the plus minus. The area represent the distance. Okay? The area represent the distance. So these are the informations related to graph. And now let's see part 2. Okay, part 2. The constant accelerations formulae. Constant acceleration formulae. So what we have here, we have the Stewart formulae. So the formulae for motion with constant acceleration are as follow. V equal to u plus at. So V, of course, make sure you know all the meaning of the symbol here. So u is the initial velocity. V is the final velocity. And then A is the constant acceleration. So constant acceleration means the acceleration must be the same throughout the whole journey. Constant acceleration. S is the displacement. And T is the time in second. Okay, so there are 5 quantities here. And in order to use the formula, you need to choose a suitable one based on the information given and based on the question asked. Okay, so let's say, for example, when should you use the first formula, V equal to U plus AT? So when there is no S. No S. You see, out of the 5 quantities here, S is not in the formula. So that means when the question gives you no information on displacement, and when the question never asks for displacement as well, then you can use the first formula. So which means no information and the question never asks for displacement, then you can use the first formula. The second formula, S equal to U plus V over 2 times T. So we can use this formula when there is no acceleration. No acceleration, it means the information has no acceleration given and the question never asks for acceleration. Then you can use this formula. The third formula is suitable to be used when there is no final velocity. And the fourth formula is suitable to be used when there is no time. And the last formula is suitable to be used when there is no u. Okay, so these are the formula that can be used to calculate whatever they ask. Okay, so out of the 5 quantities here. And when you use this formula, remember, A is a constant acceleration. S is the displacement from the starting position, T at time T, and velocity is the velocity at time T, which is the final velocity. U is the velocity when T equal to 0. Okay, so just keep this formula first and we move on. So let's see here, using a non-zero initial displacement. So that means they don't start from the origin. So if S equal to S0 when T equal to 0, replace S in each formula with S minus S0. That means, for example, if the initial displacement S0 is equal to 3 meter. That means the particle start from 3 meter from the origin. Start from 3 meter. Imagine you have a origin here, but the particles start at 3 meter. The particles start moving from here. Okay, start moving from here. So let's say this is the distance in meter. Start from 3 meter. So let's say this is the S0, the initial displacement. Then your formula, let's say the first formula, V equal to U plus AT. This is not affected because there is no S. The second formula, which is just now the Suet formula. The second formula, which is S equal to U plus V over 2 multiplied with time. Okay, so this formula, and this formula, you have to change it to S minus 3 equal to U plus V over 2 multiplied with time. So the S has to change accordingly, has to change it to S minus S0. So let's say one more example. The next one, the formula given is S equal to UT plus half AT square. So now it becomes S minus 3 equal to UT plus half AT square. And let's say the next one, they give V square equal to U square plus 2AS. So it becomes V square equal to U square plus 2A S minus 3. And let's say the final one, S equal to VT minus half AT square. So it becomes S minus 3 equal to VT minus half AT square. So the formula changed accordingly. So now let's move on. Number 3, vertical motion under gravity. Okay, so again, when it's vertical motion under gravity, we can use 5 of this formula as well. But you have to remember one thing, the acceleration due to gravity is vertically downward and is often taken to be 10. The value 9.8 is also used. So in our Cambridge syllabus, we use for mechanic we use 10. Okay, for mechanics. Of course, for physics we use 9.81. So for mechanics we use 10. So the 10 is replaced here as the A. Okay, A. So the acceleration is 10 now. Always draw a diagram and decide in advance where your origin is and which way is positive. So that means if you use A as 10, right, that is a condition. That means you assume downward is positive. Okay, you know acceleration due to gravity is acting downward. So if you use A equal to 10, right, that means you assume downward is positive. So if you assume upward is positive, then your A has to replace with negative 10. Okay, so I write down. So for the situation here, okay, if you assume downward as positive, and then A equal to 10. Acceleration due to gravity is 10. If you assume upward as positive, then A equal to negative 10. So acceleration due to gravity is negative 10. Because acceleration due to gravity always act downwards. So next one. Make sure that your units are compatible. That means all of them must be the same unit. For example, all in seconds. Okay, so Part 3, general motion in a straight line. Okay, so this is related to differentiation and integration. So you can see here, if you have S, you can call it position, but sometimes we call it displacement also. Okay, so it depends. So S. So you differentiate the displacement, ds dt, you differentiate with respect to time, then you will get velocity. So of course the displacement is given in terms of t, so something like this. For example, s in terms of t, s equal to 3t squared minus 7t plus 1. Okay, so something like this. That will give you s in terms of t. Then you have to differentiate. Velocity is ds dt. Then you get 6t minus 7. So you have to differentiate it. And after that, you can continue with this part. Acceleration is dv dt. That means you differentiate this again. So acceleration, for this case, acceleration is dv dt. So you differentiate 6t, you get 6. So that is how functions of displacement can be differentiated to find velocity function and can find acceleration functions. So if you are given with acceleration, let's say, for example, acceleration equal to 3t minus 2. 3t minus 2. So if acceleration is given, then you want to find velocity, you have to integrate the acceleration. So for example, for this case, acceleration is given, and now you integrate 3t minus 2. Then you will get 3t squared over 2 minus 2t plus c. So of course, you have to find out the value of c over here. So normally they will give you some information, like they will give you at the beginning the velocity is, let's say, 6. Okay, so let's say when t equal to 0, the velocity is 6. Okay, they will give one. So what to do with this information? We use it to find c. Okay, we use it to find c. So currently our v is equal to 3t squared over 2 minus 2t plus c. So v equal to 6, t equal to 0. All this end up with 0. So hence your c is 6, and hence your velocity is 3t squared over 2 minus 2t plus 6. So that is the velocity formula with the c found. Okay, so if we continue this process, when acceleration is integrated, we get velocity. And now you want to find position or displacement, so you integrate the velocity. By integrating the velocity, you get displacement. Okay, so for example, if I continue this over here, s equal to integrating 3t squared over 2 minus 2t plus 6 dt. So you get 3t cubed. So you have to divide by 3. 3 and 2 multiply, you get 6. 2t squared over 2 plus 6t plus c. Simplify this, t cubed over 2, t squared, 6t plus c. So you have a c again, and you have to know what value should be taken for this case. So sometimes the question will give it in this way. So that will give you information like t is the time in second after the particle passes the origin. So that will give something like this. That means we start counting the time when the particle stay at the origin or passes through origin. So that means at t equal to 0, your s is 0. Okay, your s is 0. We start counting the time when the particle reach origin. Okay, so it means that, and we use this to find c. So we substitute this into the previous equation. So you get 0 equal to 0 minus 0 plus 0 plus c. You substitute there. Okay, and you get c equal to 0, and hence your displacement equation is t cubed over 2 minus t squared plus 6t. Okay, so that is how we get the displacement function in terms of t. Okay, let's see this example. The velocity in meter per second of a model train which is moving along straight rails is v equal to this. Okay, so this is a velocity function in terms of t. Find its displacement from its initial position after time t. So to find displacement, we have to integrate. So we have to integrate. So what we do here is s equal to integrate velocity. So we integrate 0.3 t squared minus 0.5 dt. So by doing integration, you will get 0.3 t cubed over 3, 0.5 t plus c. And then you get 0.1 t cubed minus 0.5 t plus c. Okay, so now we want to find the value of c. Okay, we want to find the value of c here. So let's say the question never said anything about this. So this part, displacement from its initial position. Displacement from its initial position. It means to find the train's displacement from its initial position. We can put s equal to 0 when t equal to 0. So that means you substitute 0 inside. 0 equal to 0 minus 0 plus c. So you will end up with c equal to 0. And hence your s is equal to 0.1 t cubed minus 0.5 t, and that's all. Okay, so part 2 is kind of simple. We just substitute 3 into the functions. So we substitute 3 like this. Then you count, and at the end you will get 2.7 minus 1.5. Okay, you get 1.2 meter. Okay, so just like that. Okay, this is a simple question. And now let's see the next one. Number 3, the area under a velocity time graph. So if you have a velocity time graph, we already learned area under a velocity time graph represent displacement. But the thing is, sometimes they don't give a straight line graph. If a straight line graph is given, finding the area, you can use formula like area of rectangle, area of triangle, or area of trapezium. But if they give you a curve, to find the area under the graph, we have to use integration. So you can see here, the displacement is the area under the graph, where you integrate from t1 to t2, integrate the velocity functions given, that will give you a quadratic functions for example, then you just integrate it and you will get the value, and that value is the displacement. Okay, so now let's see the next page. Okay, let's see the question here. A car moves between two sets of traffic lights, stopping at both. Its speed v meter per second at time t is modeled by this formula. Okay, so find the times at which the car is stationary and the distance between the two sets of traffic lights. Okay, so we are looking for times and the distance. Okay, so first of all, to find the times at which the car is stationary. So the keyword here is stationary. Stationary means v equal to 0. So v equal to 0, and we substitute v equal to 0 into this formula. So you will get 0 equal to 1 over 20 t 40 minus t. Okay, so I bring the 20 to the left, so it's divided by 20 currently, and now I bring it to the left, it become multiply, and 0 times 20 just disappear, and end up with t 40 minus t. So your time is hence 0 or 40. So this is the time where the car stops. Okay, so that is the first part. Okay, the question asks for the distance between the two sets of traffic lights. Okay, now imagine that what we have here is a quadratic. It's a quadratic function. Okay, it's a quadratic function. So if you go and consider the t square term, the t square term is actually a negative term. So imagine if I expand it. So if I expand the function, I will get, this multiply with this, and then multiply with that. So I will get 20t minus 1 over 20. So no, it's not 20t, it's 2t. It's 2t. 40 divided by 20 is 2. 2t minus 1 over 20t square. Okay. So what am I trying to say is the t square term is taking a negative coefficient, and because of that, the graph should be a graph with this kind of shape. We call this set phase graph. Okay, set phase. Okay, set phase. Okay, so let's see the graph here. We know that we will have 0 and 40 with, as you can see from the previous working, right? When t equal to 0 and when t equal to 40, the velocity is 0. So that means the graph passes through these 2 points, and then it is a set phase graph. So it's like this. So vt. Okay. Now, in order to find the distance between the two sets of traffic light, of course you have to know that the traffic light stay at here, at this point, the traffic light here and here. Okay, so to find the distance, you have to find the area. And to find this area, we have to integrate. Okay, so we have to integrate. So because of that, you can see working like this. Distance equal to integration of the from 0 to 40. You put the velocity function inside. So I will put the expanded form. Expanded form is easier to integrate. So like this, dt. Okay, then we do the integration here. 2t squared over 2 minus 1 over 20 t cubed over 3 for t 0. And let's move on. Simplify it first. T squared minus t cubed over 60 for t 0. And then you substitute with value. For t squared, 40 cubed over 60 minus with 0. And you will end up with, okay, let's say 40 squared, 40 cubed over 60. So you will end up with 533.3 meter. Okay, so that is where the integrations is used to find the area under the graph, which is a curve. Okay? If it's a straight line, we don't use integration. We just use area of rectangle, trapezium, or triangle. Okay, so settle. We have finished up all the theory. So now we can start doing the past paper. Okay, let us look at these questions. A cyclist travels in a straight line from A to B with constant acceleration 0.06 meter per second per second. Okay, so let us draw out the situation. So I draw a straight line. So from A to B, constant acceleration 0.06. So of course, what am I trying to say is, when they give you constant acceleration, that means the Stewart formula, the 5 formula just now, that may be applicable. Okay, so we just take a look first. So we have A, and now his speed at A is 3 meter per second. So that is counted as the U equal to 3. And his speed at B is 6 meter per second. So V equal to 6 meter per second. Okay, let's say just ignore the unit. We just need to make sure they have the same unit only. Okay, so let's look at part A now. Part A, find the time taken by the cyclist to travel from A to B. Okay, to travel from A to B. So if you look at the information available, so we have A, we have U, we have V, and we need to find T. So no S. No S, no S involved. The question never asks for S, and the information never give S. So S is not involved. Then the formula that we're supposed to use is V equal to U plus AT. So this is the formula with no S, and we substitute 6, 3, 0.06, and we find T. 3 equal to 0.06 T, and we get T equal to 3 over 0.06. Okay, 50. Now 50 seconds. Okay, so this is part A. Now part B. The distance AB. The distance AB. So which means you have to find S. So you have to find S. So you have to find S. So we have plenty of information now. We have A, we have U, we have V, we have T, we have to find S. So in that case, you can just choose any formula you like. So because we have all information available, so let's say I choose this formula. Let's say I use V squared equal to U squared plus 2AS. Using this formula has its own advantage, because just in case if you make a careless mistake with your time, so this part is not affected, because this formula has no time. No timer. Who knows, you make careless mistake here, and then if you are using other Seward formula, the formula has time over there, and it involved, and you put the wrong value here, then it makes the displacement wrong also. So this formula doesn't involve time, and we are safe from making mistake. Okay, so we substitute 6 square, 3 square, 2, A is 0.06, S is unknown. Okay, so we have to count this. 36 equal to 9 plus 0.12 S. 25. Okay, so S equal to, so we just count this, 36 minus 6, divide 0.12, 36 minus 9, divide 0.12, so we get 225 meter. Yeah, so that is the distance AB. Distance AB. Yeah. So the distance is same with the displacement. If the cyclist is moving in one direction, of course, if they change direction, if they U-turn, then distance and displacement will be different already. Yeah? So you have to remember this S is displacement. For this case, it is also, this value represents distance as well, because the cyclist never change direction. It's just moving forward. Now let's move on with part 2. Okay, part 2. Okay, so let's see the question first. A car leaves A at the same instant as the cyclist. Okay, that means start from here. Okay, now the car starts from rest and travel in a straight line to B. Travel in a straight line to B. So let's put the informations in this way. Okay, so for part 2, okay, let's say I use blue color to represent car. So start from rest, U equal to 0. U equal to 0. And after that, travel in a straight line to B. Okay, we look at the question again. The car reaches B at the same instant at the cyclist. Same instant. So that means 50 seconds. 50 seconds. So the cyclist takes 50 seconds to reach B. So the car takes the same time. So we write down first. Time equal to 50 seconds. So we continue the questions. At time t second after leaving A, the speed of the car is kt square meter per second. So the speed of the car. They give you function in t, so we have to put it in this standard way. We put it in v equal to kt square. So where you have to involve some integration or differentiation of this to find out displacement or acceleration. So where k is a constant, find the value of k. Find the value of k. So with this kind of information, we have to find the value of k. Okay, so ut, and we have this. Okay, so in order to find k, so what can we do is we have to know also, as you can see, from the car move from here to here as well, and the distance move or the displacement is 225 also. So this 225 can be used by the car as well. So I just bring forward. So S is also 225 because it's A and B, in the distance between A and B. And now with the displacement, then they will give us an idea where we have to do integration to find the displacement. Okay, so we do like this. S equal to integrate velocity so we get kt cubed over 3 plus c. Okay, so this is the displacement function, and we have to find c first. Okay, we have to find c. So now to find c, let's say I bring it here. So what we need to know is this sentence. You can see the cursor here. At time t second after leaving A. So that means we assume A as our origin. So the time start counting after leaving A. Okay, so that means initially the car stay at point A. Initially the car stay at point A. Or even this part tell us the same idea. So you can see here, this particular part here, the car starts from rest. The car leave A at the same instant. They start from A, start from A. Okay, so which means, okay, we write down the information. When t equal to 0, the displacement of the car is 0 because it starts from A. And now we consider this equation, we substitute accordingly. 0 equal to k0 cubed over 3 plus c. 0 equal to c. So we get ready. S equal to kt cubed over 3 plus 0. Okay, we don't write plus 0. So now how to find the k then? We have 225 is the moment when the car reach B, and we have time also. The time is 50 seconds when the car reach B. Okay, so at B, so S is 225, K is unknown, time is 50 over 3. So we just need to solve this equation, and then you will get the values of K. So 225 times 3 divided by 50 cubed. Okay, so we get K equal to 0.0054. Okay, so that is the value of K. And now let's look at, okay, this part we get 4 marks. Now the last part B, the speed of the car at B. The speed of the car at B. Okay, now in order to find this, we can use this equation, V equal to kt squared. Okay, so part B, V equal to kt squared. The k is 0.0054 t squared. So at point B, right? At point B, our time is 50. So V equal to 0.0054 50 squared. And then by pressing calculator, we will get 0.0054 times 50 squared. So we will get 13.5. 13.5 meter per second. Yeah, so that is how we do these questions. Okay, so let's see this question. This question is about vertical motions. So gravity is affected there. Okay, now let's see. a particle P1 is projected vertically upwards from horizontal ground with a speed of 30 meter per second. So let's say, imagine you start from the ground, the particle P go up, so U is 30 meter per second. Okay, so let's continue. At the same instant, another particle P2 is projected vertically upwards from the top of a tower of height 25 meter. Okay, so let's say this is P1, and another particle, let's say I use red color, P2. Okay, this P2 has U equal to 10. Okay, U equal to 10 meter per second, and then this is P2, and the initial displacement is 25 meter from the ground. Okay, so now let's see the next part. Find the time for which P1 is higher than the top of the tower. Higher than the top of the tower means greater than 25. Greater than 25, huh? You know, the tower is 25 meter. So higher than the top of the tower means greater than 25. So which means the S is greater than 25. Okay, so let's say I use blue color for P1. Okay, so that's P1 and P2, the working are separated. Okay, so higher than the top of the tower means S is greater than 25. Okay, so what information we have here for P1? Okay, P1, right now, we have U equal to 30, and let's say we assume upwards as positive directions. We assume upward as positive direction, but this statement you're not going to write down. You can set on your own one in your mindset. You remember, I assume upward is positive. Okay, upward is positive, and then because of that, your acceleration due to gravity, which is always acting downwards, so it is negative 10. It's negative 10. Okay, so we are looking for the time. Okay, the time for which P1 is higher. P1 is higher than. Okay, so imagine, let's say this is the tower. Your P1 is thrown upwards, and then they will go downwards. Okay, so they want to find this particular moment until this particular moment. So which means in black color, this particular duration. So that is the duration where it is higher than the top of the tower. So we want to find that out. Okay, so let's see the information available here. We have we have U, we have A, we have T, we have S also. So SUAT, so no V, no V, then we use this formula. S equal to UT plus half AT square. Okay, so the U is 30, T is unknown, half negative 10, T is unknown again. This thing is greater than 25. That is the displacement. Displacement greater than 25. Okay, so we have to solve inequality now. 30t minus 5t square greater than 25. So we shift everything to the right. 5t squared minus 30t plus 25. Okay, so to make it in the normal way, so this is actually less than 0. I divide by 5. I get t squared minus 6t plus 5. Then I factorize. Okay, then, to solve quadratic inequality, normally we draw a graph like this, where you have 1 and 5. Less than 0 means the bottom. And then it means your time is in between 1 and 5. 1 and 5. Huh? Okay, so this is the answer. And it means, as you can see the diagram, this particular part, from the first second until the fifth second, they are above of the top of the tower. So that is first part, 3 marks. Okay, so we have done 3 marks. Now let's see the second part. The second part, they ask you to find the velocities of the particles at the instance when the particles are at the same height. So the particles are at the same height. That means P1 and P2 are at the same height. So if they are staying at the same height, that means they have the same displacement. They have the same displacement. Okay, so we have to work it out. Okay, same displacement. Okay, so first of all, we already know particle 1. Okay, we already know for particle 1, the displacement. Okay, I write down first the displacement. Okay, let's say part 2. Maybe part 2. Okay, so I do it at the side here. For particle 1, we already know the displacement's formula is ut. Okay, so we have done it just now, somewhere here. Okay, this part, which is, this is s, the where we apply this formula, right? So we get 30t minus 5t squared. Okay, so we get it from this part. Okay, I already simplified the s just now, so I just use it straight away. 30t minus 5t squared is the displacement for P1. Now for P2, so let's say P2, I use red color. So for P2, so if you still remember the note just now, where it is somewhere on page 5, at that time I said if the displacement never start from origin, if the displacement never start from origin, okay, I write down, this is on the note, page 5. If the particle doesn't starts from origin, start from O, let's say, okay, use S minus S0 to replace S. Okay, so you have to use S minus S0. The S0 is the initial displacement. So we have to apply that here. As you can see, our particle start from 25 meters from origin. I assume the ground as origin. Okay, so they start from 25 meters from origin. So I have to use S minus 25 instead. So because of that, my P2, you have S minus 25 equal to UT, okay, I'm using the same displacement formula, which is this formula, but the only thing is the S I have to adjust accordingly, S minus S0. The rest, same with this part. Okay, so I have UT now. My U for P2 is 10 T plus half. The acceleration is negative 10, as I assume upward is positive, so downward is negative 10. So T squared. So if I simplify this, S minus 25 equal to 10T minus 5T squared. So at the end, let's say I change it to S. Okay, S equal to 10T minus 5T squared plus 25. Plus 25. So I get the equation for P2 already. Now, the question said, you see the question again. The question said the particles are at the same height. That means they have the same displacement. So I have to equal between 1 and 2. Okay, so I have to take 1 equal to 2. So I will have 30T minus 5T squared equal to 10T minus 5T squared plus 25. Okay, so after that, I have to solve the quadratic equation. The power 2 term just cancel off. So it become a power 1 equation. 20T equal to 25. So T equal to 1.25. So this is the time where both particles staying at the same height. And we are not looking for the time. If you can see the question again, we are looking for the velocities. So P1 and P2 will have their own velocity. We have to find it separately. Okay, so now let's say we start from P1. Okay, P1. The time is the common time because they start at the same time, So both particles start at the same time. The time is the common time, but when we count velocity, don't mix up the information. So for P1, I use blue color again. So to find the velocity, let's say I use V equal to U plus AT. So the U is 30, the A is minus 10, the time is 1.25. Okay, then we get the V. So the V is going to be 17.5 meter per second. Okay, that is for P1. So for P2, let's say I use V equal to U plus AT again. So the U, so again, like what I mentioned before, this formula has no displacement. So the S minus 25 is not affecting here. So we just do it like usual. So U is 10. A is negative 10. T is 1.25. Okay, so 1.25 and 1.25. So at the end, V equal to negative 2.5 meter per second. So these are the answer for the velocities of both particles. Okay, now let's move on to part 3. Yeah. Okay, part 3. Let's see the question. The time for which P1 is higher than P2 and is moving upwards. So many conditions. Higher than P2 and is moving upwards. Okay, so you know P1 will move downwards after a particular moment. After the maximum height, they will start moving downwards. Okay, so we want the time in between. Okay, the time in between. So first of all, let's deal with this part. P1 is higher than P2. P1 is higher than P2. So we already find this. P1 has this displacement formula. P2 has this displacement formula. So we just want to make equation 1 greater than equation 2. Greater. So, okay, greater. Now let's do it here. So if you have 30, I call it part 3. Okay, so if you have 1 greater than 2, right? So basically it is 30t minus 5t squared greater than 10t minus 5t squared plus 25. So it is actually the same working as here. As you can see, this part, it is just now it's equal, but now it's greater. It will be the same working one. So, first we can just cut both sides, and then we end up with 20t greater than 25, t greater than 1.25. Same working like just now. So that means when the time is greater than 1.25, P1 is higher than P2. P1 is higher than P2. Okay, so the second condition given here, you see the question again. Okay, we already settled the first part, which is here. The time for which P1 is higher than P2, we already know t is greater than 1.25. And now the second condition given by the question is P1 is moving upwards. P1. Okay, P1 is moving upwards. So P1 is moving upwards all the time until here. At this particular point. Okay, at that particular point, it is moving upwards. After that particular point, this maximum height here, after this point, then it starts moving downwards. So we need to find this particular time. Is kind of easy to find actually. At maximum height, v equal to 0. At maximum height, v equal to 0. So let's write down here. At maximum height, v equal to 0. So we have v equal to u plus at. So v is 0, u is 30, a is minus 10, and then t is unknown. So we want to solve this. T equal to 30, okay, 3. T equal to 3. T equal to 3 is where the particle P1 reaches the maximum height. Okay, so now combining these two information, then we will end up with the answer. From 1.25 until 3, the particle P1 is higher than P2 and at the same time moving upwards. So this is the time. Greater than 3 we can't take already. Okay, because Even equal to 3, we can't take also. Equal to 3 is where it is stationary at the maximum height, which means they are not upwards anymore. It is stationary. No upwards and no downwards at that time. So after 3 is downwards, we can't take also. Okay, so that is the answer for these questions.